So in this section, we're going to talk about torque. Uh, Torque is the rotational equivalent of force. So if you remember real quick, forces cause things to accelerate. If you remember Newton's second law, F equals ma, if you've got a net force, the object will accelerate. Likewise, torque is the rotational equivalent of that. But what does torque do? Torque, represented by the Greek letter tau, causes things to angularly accelerate, begin to rotate, or to increase the rotation rate or decrease the rotation rate. What's the definition of torque? Torque is force times radius times the sine of the angle between those two. And you might say, wait a second, how do you draw the force? Well, the radius is always drawn from the pivot point to wherever the force is applied. So in this case, this would be the radius, and the angle you can just do this way. Here you get maximum torque. Remember, sine of 90 degrees would give you 1. And you get even more torque if you increase the radius. So again, radius drawn from the pivot point. In this case, it's going to rotate around the center of that bolt, and you can very quickly calculate this. I want to mention this just real quick. We'll spend a little more time talking about it later. A lever arm. A lever arm, you can also just calculate this by finding the perpendicular distance. This is the lever arm right here that I'm drawing in dark color. It's the perpendicular distance between the force and the pivot point. So if you took this line along which the force is acting and worked your way backwards, you would find some point here where it's exactly perpendicular. This distance here is the lever arm. It turns out the lever arm is equal to the radius times the sine of theta. And oftentimes it's a much faster way of solving it. So usually we just write torque this way. So torque, as I mentioned before, this is the Greek letter tau. How do you draw a tau? Tau is sort of like a pie standing on one leg. If you think about normally when you draw a pie is like squiggly with two lines. A tau is a squiggly line, but just one line down. My font here puts a little curly Q at the end here. That is not necessary. But that's the symbol we use for torque. So take a quick look at this one. I want you to think about it. This is a conceptual question. Which of the following screwdrivers would provide the most torque to turn a screw if you applied the same force to the handle? This is a stubby screwdriver with a big head on it. And this one's a long screwdriver with a small head. And again, quick reminder on this one, torque is defined as force times radius times the sine of theta. But what in the world would you do in this case? Stop for a second in the video and just think about it. Talk to your neighbor and see if they agree on this one. Which one of these would provide more torque? The correct answer on this one, ironically, is if the force is applied to the outside edge of the handle and the pivot point's the middle of the handle, this one actually has a greater radius than this one. So the stubby one even would actually produce more torque. Why? Because it has a greater radius than this radius. And when you plug it in up here, you get more torque for this one. So this one is the correct answer. One quick note about this, and I don't want to spend too much time on this one, but counterclockwise torques are always defined as positive. So this would be a positive torque because why? This force is trying to rotate this bolt counterclockwise. And likewise, this one's clockwise, and we're going to consider all clockwise torques to be negative. There's a right-hand rule that goes along with this that I should show you, but I'll show it to you another time if you're watching this video. Just remember, counterclockwise torques are positive, clockwise torques are negative. So we can actually do some calculations with torques. Take a quick look at this situation. We've got a wrench turning a bolt. In this case, our pivot point would be the center of the bolt right here. Again, remember the equation for torque: force times radius times the sine of theta. And in this case, the angle between the force and the radius is 90 degrees. So solving this, torque equals force times radius sine theta. Force is 100 newtons. Distance is 0.2 meters or 20 centimeters. Sine of 90, which of course is going to be 1, and we end up with 20 newton meters. Positive, why? Again, because this is going to rotate, or this force is going to rotate this counterclockwise, or would tend to rotate it that way, which is in the positive direction. What about this one? Here, the angle is 30 degrees between the radius vector and the force. And a lot of people panic about this. They go, wait a second, should I use this angle going this way? Or should I measure the angle going this way around this way, which would be 150 degrees? Or should I, actually 210, or should I go this way, which is 150 degrees? Well, it turns out the sine of all three of these angles is exactly the same. So it doesn't matter how you measure the angle, you'll get the same answer. So solving this one, same situation, we have the same force, same radius, but now we have the sine of 30 or 150 or 210. And you'll discover in this case, it's positive 10 newton meters. Still positive because it's going to rotate again in counterclockwise direction. If it was clockwise, it would be negative 10. What about this case? The angle here is 180 degrees, or 0 degrees, depending on how you look at it, between these two things. If you solve this one, sine of 180 or sine of 0 is 0. So the torque in this case is 0. And you don't have to think about positive or negative because this torque doesn't rotate it clockwise or counterclockwise. What about this one? Well, this one's a little bit more exciting. We've got two forces acting on it. This force, which is going to try to rotate this thing counterclockwise, and this force, which is going to try to rotate it clockwise. How do you figure out the net torque? We're going to do this individually. We'll figure out the torque due to this force first. Actually, probably this one first, F1. And then figure out the torque to the other force, and then add them together to figure out the net torque. So first of all, let's do F1 over here, the 8 newtons. The 8 newtons, how far is that away from our pivot point? Well, it's 2 plus 3, or a total of 5 meters away. The angle is 90 degrees. And so what's the torque here? Negative 40. Why negative? Again, because we're trying to rotate this whole thing clockwise around that pivot point O. Now for F2, just plugging in our numbers, 12 newtons, it's 2 meters away. Sine of 30, this is trying to rotate it counterclockwise, so this is a positive torque. What's the total or net torque around point O? Well, we just have to add those two together, and we get negative 40 plus 12, or negative 28. Which way is this thing going to rotate? It's going to rotate clockwise. Notice the negative torque means it's going to rotate that direction. The 8 Newton force wins over the 12 Newton force, if you want to think about it that way. The lever arm I told you meant a little bit longer, or again here, it's just that perpendicular distance right there from along the line of force. It turns out if you look at this right triangle, if this is a right angle here, if this distance right over here is r, some of you will see it real quick here, sine of theta is going to be equal to the opposite side, which is d over r. Or rearranging this, r times sine theta is equal to d, which is why we can do this kind of creative thing. If this side is equal to that, remember that torque was defined as force times radius times sine of theta. Well, in this case, this distance right here, which we call d up here, is equal to r times theta. So we can simply replace this whole thing here with just this d over here. This actually is useful, and I'll show you an example in just a few moments. It makes life a little bit easier in some times. Like, for example, this one. You kick a soccer ball, and your force is directly through the center of mass. Remember, the center of mass is the point that things tend to rotate around? So that's our pivot point this time. Will this ball begin to rotate? And if you think about it, if you think about the torque, the answer is no. Why? There's no torque on it. Force times distance. There is no perpendicular distance between that line of force and this. So what's this ball going to do? It's going to accelerate this way, but it's not going to rotate at all. What about this case? Well, for this case, you're kicking along this line right here. There is a distance here. Which way will this ball rotate? Well, it's going to both accelerate this way, because you've got a net force on it along that line. Oh, there's D. I drew it on there anyway. And you're going to have a torque. And that torque is going to cause this ball to rotate in this direction. So it's going to rotate counterclockwise as it's accelerating that way. So you get a nice you get both rotation and some motion to it. And this goes in, or gets definitely applied in this case here. So take a look at this before we get going. Will F sub A produce a torque on this? Now here's our pivot point. It's the center of mass. They listed as C sub M. Will this generate a torque? Well, this is like our soccer ball being kicked right through the center. No, this will not generate a torque at all. What about F sub B? Again, its line of force is right along here. There is no perpendicular distance between that and the center of mass. This will not generate one either. Likewise with C, you can probably see it. But what about D? Take a look at D again. I'm going to erase the other ones here just to clean things up a little bit. D, the line of force is straight up. And if you work it out real quick, yeah, there is a distance between that and that. And so, yeah, F sub D will generate some torque. So yes, F sub D will. And same thing is true with F sub E. Here, F sub E, the perpendicular distance would be something like this. And yeah, this one will also generate a torque. And the same thing is true with F sub F. This would be the perpendicular distance between its line and that. And the same thing is also true for F sub G. I can't draw these, sorry, they're on top of each other. And then F sub H is a definite no. Why? It's right along here, so this one's a no. But the other ones are yeses. These will all generate torques. So on the answers, this one, F sub D, F sub E, F sub F sub F, and F sub G. And then if all the forces are equal, which one of these four that we have little check marks by is going to generate the most torque? Well, if we use the idea that torque is equal to either force times radius times sine of theta, or our new equation, I told you this would come in handy, our new equation, which is just force times that lever arm D, which one of these is going to produce the most torque? And hopefully you can see it's this one, because it has the greatest D. If force is all the same, this one's going to produce the greatest torque. All right. A little bit of seesaw action here. Take a look at this real quick. These two children are on a seesaw and they're balanced. How is that possible, even though they have different weights or different force of gravity on them? The answer is that the net torque here must be 0, which means the counterclockwise torques in magnitude must equal the clockwise torques in magnitude. If we solve this real quick, the girl has a counterclockwise torque. Here's the force of gravity on her. Here's her distance away. The angle here is 90 degrees. Is going to equal the torque due to the boy. His force, 500 newtons. His distance, 1.5 from the pivot point. Here's our pivot point. Times, again, sine of 90. And if you work that out, oh yeah, it's 750 equals 750. Yeah, their two torques are equal in magnitude. And you could quickly work this out. Now, what about this case? What if instead we put the girl on a swing and tied her so she was 4 meters below or 5 meters from the pivot point? How, in this case, how far should the boy sit away from this one? And I want you to think about this for a brief moment before I answer it. Believe it or not, the answer is it's exactly the same. Why? The force of gravity is still acting here. The force of gravity on the girl, you can just think about it as acting where that swing is attached to here. What's the distance over here going to be? Believe it or not, it's still exactly 1.5 meters. Yes, you could also solve this. You could think about this as the lever arm, or you could have taken the 5 meters and calculated the angle between here using trig and then taken the sine of it. But believe it or not, it would have given you the same answer no matter which way you did it. What about this seesaw here? In this case, you've got a 100-kilogram person there, and they're 1.2 meters away from this pivot point. How far away should a 40-kilogram child stand so that the net or the total torque is equals 0? Again, my little quick shortcut, if you just think about the counterclockwise torques have to equal the magnitude of the clockwise torques, you can solve this one. In this case, the force of gravity on the 100-kilogram person is going to be 1,000 newtons, and it's going to be acting straight downward here. And so that force times that distance, and yes, the angle here is going to be 90 degrees, is equal to the force over here, which is going to be 400 newtons, times the unknown distance, which I'm just going to call x over here. And the angle, again, 90 degrees. Solving this one, we end up with 1,200 equals 400x, or x in this case should be 3 meters away. If that person stands 3 meters, their two torques are going to be equal and it will balance. What about this one? This time there's two children standing on the other side. One is standing 0.8 meters away, the other one's standing 1.2 meters away. The pivot point's still here. In this time, I want to know how far this person, the adult, needs to stand away to actually balance it. We're going to do the same trick. Torque counterclockwise equals torque clockwise. The only big difference this time is we actually have two clockwise torques. Both of these forces are going to try to rotate the seesaw clockwise. This 400 newtons, that's the force of gravity on this 40-kilogram child, and this 400 newtons, which is the force of gravity on the other 40-kilogram child. And that's got to be balanced by the torque produced by the force of gravity on this child, or the adult, which is 1,000 newtons. Plugging in our numbers, 1,000 times x, the unknown distance up here, has to equal 400 times 0.8, that takes care of that child, plus times sine 90 plus 400 times 1.2 meters, that's the other child over here. Sine of 90 for all of these is going to be 1. And so you end up with, may have this out of order. I do. Shoot. 320 plus 480 equals that. Adding those together gives us 800 equals 1,000x. Dividing both sides by 1,000, we get 0.8 meters. Hopefully that makes sense. Take a look at this next one. This one's more conceptual. Rank these situations from greatest to smallest force required to maintain equilibrium. So for A, there's the force of gravity in all the masses. It's all the same. And now we need to figure out the forces. Well, for A, we end up with this. If you think about it, here's our pivot point. The counterclockwise torque is going to be this unknown force times 4 units of distance is equal to force of gravity times 2. So in this case, force of gravity, or the unknown force, is going to be the force of gravity divided by 2. How about B? Well, similar in this case, except now the mass is only 1 unit away. So if we solve this, we end up with that. Could you please try it for the other ones or pause the video at this point before I write my answers up here? And I've got to think about it real quick. And if you restart already, in this case, I think the force is going to be equal to 3/4 of the force of gravity. And for the next one, assuming the beam has no mass, this one's going to be the same as the one above it. Force is going to equal the force of gravity over 2. This one, interesting, the force is going to equal 2 times the force of gravity. And that is also going to be the same for this one. So if you rank them from greatest force to smallest force, you should end up with E equals F are the two greatest, they tie, followed by, let's see here. We got, I guess the 3/4 is probably the next one. Followed by, okay, hold on a second. So that takes care of that one, and that one. Followed by these two, which tie, A and D. That's a really bad A. And then followed at the end, the smallest one is B. Hopefully that makes sense. What about this situation? Which one of these forces would be greater? In this case, you've got a 200 kilogram mass hanging on the end of this stick. And this one's interesting. If you think about it, you're going to be using this equation. In this case, it's easy. You're like, oh, the angle here is 90. This is super easy. We can very quickly solve it, and you can figure out the force in this case would just be 667. But what about in this case? In this case, we've got this unknown angle theta. We can't even calculate it. And we've got this unknown angle theta. We can't calculate it. But some of you may notice already, what's true in this case? Those two thetas have to be equal to each other. They're kind of like opposite interior angles, which hopefully most of you know. So whatever theta is, sine of theta here is going to equal sine of theta there. And so if you solve this, you'll get exactly the same answer. Kind of a trick question in this case. The two of them are exactly the same, which hopefully should help you analyze this one. So the angles here are not critical. As long as the two angles are the same, we can solve this. So take a look at the first one here. It's 1,000 times 1 is going to equal the force times 3 times whatever the angle is. And so you'll just end up with that one is 333. Whoops. And now what about the other ones? You can very quickly work it out. In this case, this is going to be, pause the video if you want to try it first. It's going to be 1,000 times 3 equals force times 1. The force in this case is going to be 3,000 newtons. For this one, it's just going to be 1,000 newtons. And now they do a little trick on us. They change the hanging mass. So now it's 200. So now we got 2,000 is the force of gravity. This is going to be 2,000 divided by that. It's about 667 to 3 sig figs. This one is going to be 2,000 newtons. And this last one is going to be 6,000 newtons. And I won't write the rankings down. You can sort of see it at this point. Which one's the largest? The 6,000, and then we work our way down 2,000, 1,000, or sorry, 6,000, 3,000, 2,000, 1,000, 667, then the 333. Talking about torques and balances, I just want to show you this quick little video clip. This is Alexander Calder. Used to make these very large mobiles that would balance and actually do art. You actually see these in lobbies of some large buildings. All it is the idea that you must balance, so counterclockwise torques have to equal clockwise torques. Talking about that, here I want you to create your own mobile. The rods here have no mass. What we want to do, though, here is connect these together. So imagine we start from the bottom. You've got two 1 kilogram masses hanging at both ends. Where could you suspend this bottom one from so it would balance? The answer is at point B. If you tied a string to that point and then hung it, it would balance. But now where can I tie this to the next one up so that this one balances? Well, basically, this is like now a total of 2 kilograms. Where could I put 2 kilograms on here so it would balance with the other 2 kilograms? The answer is over here at E. Now I've got basically 2 kilograms tied there. I've got 2 kilograms there. And if I suspended it from point F, it would now balance again. Again, normally these strings would be straight when you actually hang them. This is now 4 kilograms. Where could I put 4 kilograms on this next one to balance? And you might say, oh, I, and I'll balance it with J. Well, that won't work because I'd have 4 kilograms there, 2 kilograms there, equal distance, won't balance. But what I could do is this. Put the 4 here, and now if I balance it from here, 4 times 1 is equal to 2 times 2, it'll balance. This is now a total of 6 kilograms. Where can I put 6 kilograms on this next one so it would balance? Some of you already can sort of see it. I'm going to have to attach it over here at O. I've got 6 kilograms tied to O. If I balance it right here at N, it'll balance. Why? 6 times 1 is equal to 2 times 3 units of distance. It'll balance. Finally, now I've got 8 kilograms here. Where can I balance it from the top part? This one's a little tricky. You might have to actually think about it a little bit. But if you put it over here at R, it'll balance. If you, and only if you, hang it now from point Q. You might say, wait a second, how's that work? Well, 8 times 1 is equal to 2 times 1 plus 2 times 3. That's 6 plus 2 is 8, is equal to 8 times 1. It will balance. And if you then hang it from this hook up here, the whole thing will balance level. That one's tricky. I do want to do 1 or 2 more with these with you. Your muscles in your body are actually quite interesting. For these, think about your pivot point as being your elbow right here. And in this case, you're holding onto a bowling ball. That's 50 newtons. That's actually the force of gravity on it. That's not its mass, not in kilograms. How much force do your muscles need to exert upward? Oh, red on red, not very good. Down here kind of gives you another diagram of it. Here's your pivot point. Treating the arm as just a lever. This distance right here between the elbow and your muscle is 3 centimeters, or 0.03 meters. We can solve this one. Oh, I did draw a pivot point there. Counterclockwise torques equals clockwise torques. In this case, the force your muscle exerts times the distance times, I know it's not quite perpendicular, but we're going to pretend it is equal to the force of gravity on the bowling ball times the distance it's away times the sine of 90 as well. And if we solve this, whoops, again out of order, you'll get something like this. Oh, brain break. If you want to try this, you're going to insert 2 different pairs of letters into the blanks below to form 2 common uncapitalized English words. So in this case, you've got CAU blank blank and CAU blank blank. What 2 consonants could you put in both of these to make 2 English words? Give these a try. They're a little challenging. Pause the video now if you don't want to see the answers right away if you want to try it. Here are some of the answers. Caulk and cause, pliant and plight, destiny and destroy, egress and excess, shorten and smarten, smarten apparently is a word, ampere, which is a unit of electric current, and ampule, which is a container. All right. With that, have a great night. You should be able to work on the worksheets and the homework without any problem. Good luck.